There is a quiet revolution happening in astronomy. For the first time, telescopes are not only finding distant worlds. They are beginning to read the thin, invisible envelopes of gas that surround them. An exoplanet is a planet orbiting a star other than our Sun. Most are so far away that even the largest telescope cannot see their surface directly. Yet a planet can reveal itself in a remarkable way, by passing in front of its star and leaving a chemical fingerprint in the starlight. Tonight, we are following that fingerprint. We will explore how modern observatories detect atmospheres, why a tiny dip in brightness can contain the story of an entire world, and why the search for life is much harder, and much more fascinating, than a simple hunt for oxygen. Imagine looking at a lighthouse from thousands of kilometers away while a grain of dust crosses the beam. The light changes by an almost imperceptible amount. That is the basic geometry of a transit observation. When an exoplanet moves across the face of its star, the star appears to dim slightly. The size of the dip tells astronomers the approximate size of the planet. The timing of repeated dips reveals its orbit. But the real treasure appears when the planet is near the edge of the star and a little of its atmosphere filters the light. Different molecules absorb different colors, or wavelengths, of light. Water vapor, methane, carbon dioxide, sodium, and many other gases each leave their own pattern. By spreading starlight into a spectrum, astronomers can search for those patterns and reconstruct the composition of a distant atmosphere. This is not a photograph. It is closer to forensic science. A planet may be nothing more than a few pixels, or no pixels at all, but its chemistry changes the light in a measurable way. The James Webb Space Telescope was designed to make this kind of measurement possible, especially in infrared wavelengths. Infrared light can pass through dusty regions of space, and many important molecular signatures are stronger there than in visible light. Webb also benefits from its enormous, cold, and carefully shielded mirror. The telescope must measure faint differences while looking at a star that is vastly brighter than the planet beside it. Every source of heat, vibration, and instrumental drift matters. The challenge is extraordinary. The atmospheric signal from a small rocky planet can be comparable to a candle seen from hundreds of kilometers away, while the star is more like a stadium floodlight in the same frame. For this reason, astronomers often begin with planets that are easier to study, large gas giants orbiting very close to their stars. Their atmospheres are deep, their signals are stronger, and their years may last only a few days. These hot worlds are not likely to host life as we know it, but they are invaluable laboratories. They teach scientists how clouds form at extreme temperatures, how heat moves around a planet, and how instruments behave when confronted with a complicated spectrum. Every successful observation improves the models needed for smaller, cooler worlds. Then come the sub-Neptunes. These planets are larger than Earth but smaller than Neptune, and they are surprisingly common. Our solar system has no close example, which makes them a major mystery. A sub-Neptune could have a thick hydrogen-rich atmosphere, a deep ocean beneath a steamy sky, or a rocky interior wrapped in gases produced by volcanic chemistry. Two planets with the same mass and radius might have completely different histories. Their atmospheres may even be changing now. High-energy radiation from a young star can strip away light gases, gradually transforming a once puffy world into a smaller, denser planet. In this way, planetary systems are not static collections of objects. They are evolving experiments. Rocky planets are the ultimate prize, but they are also the most difficult targets. Earth-sized worlds have thin atmospheres, and the signal from each transit is tiny. A single observation is rarely enough. Astronomers may need to watch the same system transit after transit, combining data over months or years. The star itself must also be understood. Star spots, flares, and magnetic activity can imitate or conceal atmospheric features. This is one reason the habitability question cannot be reduced to a checklist. A planet in the so-called habitable zone receives the right general amount of energy for liquid water to exist on its surface. But that zone is only a first approximation. A planet's atmosphere controls its climate. Its pressure, clouds, circulation, reflectivity, and chemistry determine whether water remains liquid, freezes, boils away, or disappears into the ground. The same orbit can produce very different environments on different worlds. A red dwarf star makes the problem even more complicated. These small stars are common and long-lived, and their habitable zones lie close in, making transits frequent. But young red dwarfs can unleash powerful flares and streams of energetic particles. A nearby rocky planet may be tidally locked, always showing one face to its star. That does not automatically make it lifeless. Atmospheres can transport heat, and the boundary between permanent day and permanent night could be a strange climate of its own. The search for biosignatures begins with chemistry, but chemistry is not a verdict. Oxygen is often mentioned because life on Earth produces much of it through photosynthesis. Yet oxygen can also build up through non-biological processes, especially around active stars or on planets that lose hydrogen to space. Methane can be produced by life, but it can also emerge from geological reactions. Water vapor may suggest an ocean, but it can also come from volcanic activity or a runaway greenhouse. The strongest evidence would be a combination of gases that should not coexist for long without a replenishing source. Even then, scientists would ask a more cautious question: what else could create this signal? Good astronomy is not the art of finding the most exciting interpretation. It is the discipline of eliminating the alternatives. This is why future observatories matter. Webb is extraordinarily powerful, but it is not a magic camera. It sees through carefully planned programs, precise calibration, and statistical analysis. The next generation of space telescopes may be built specifically to block a star's light and directly study faint planets beside it. One approach uses a coronagraph, an optical mask that suppresses the glare of a star. Another uses a star shade, a giant petal-shaped spacecraft flying far away from the telescope to cast a controlled shadow. In principle, these systems could reveal a pale point of light and separate its spectrum from the star. The distance between stars makes this difficult. A planet that looks close to its star in the sky may actually be millions of kilometers away from it. The telescope must maintain exquisite alignment while traveling through space, and the starshade would need to reposition with great precision. But the reward would be profound. Instead of relying only on transits, astronomers could study planets at many points in their orbits. They might observe changing cloud patterns, seasonal variations, and the colors of a world reflecting its star. For the first time, planetary science could become a comparative science on a truly cosmic scale. Earth would no longer be the only atmosphere whose climate and chemistry we can examine in detail. We could compare dozens of worlds and ask which physical pathways lead to stable oceans, thick clouds, or the chemical imbalance associated with biology. The most important discovery may not be a single second Earth. It may be the realization that planets come in far more varieties than our local neighborhood suggested. Some worlds may be ocean planets. Others may be lava worlds with skies of rock vapor. There may be planets wrapped in global storms, planets stripped nearly bare, and planets whose atmosphere is continually rebuilt by volcanoes and impacts. Every spectrum is a message from a place we cannot visit. It has crossed light years, passed through a telescope, and been translated into a pattern on a screen. From that pattern, humans infer pressure, temperature, clouds, and molecules, properties of worlds that no human eye has ever seen. And there is a final twist. The farther we look outward, the more carefully we are forced to look inward. Earth's atmosphere is not just familiar, it is unusual in ways we are still learning to appreciate. Its chemistry, oceans, continents, magnetic field, and living organisms are connected in a delicate planetary system. Studying exoplanets gives us alternate versions of the story. It shows what a planet might become when one variable changes: a stronger star, a weaker atmosphere, a different mass, a missing magnetic field, or a warmer beginning. The search for life beyond Earth is therefore also a search for context. We are trying to discover whether biology is a rare accident, a common outcome, or something that appears in forms we have not yet imagined. For now, the evidence arrives as faint dips, subtle absorption lines, and spectra that demand patience. No distant atmosphere has yet handed us an unambiguous answer to the question of life. But the method is working. We have moved from wondering whether planets exist to measuring what some of them are made of. And with every new observation, the universe becomes less like a collection of points and more like a gallery of living possibilities. Somewhere beyond the familiar stars, another world is crossing its sun. For a few hours, its atmosphere is writing a message in light. Our telescopes are waiting to read it.